Okay, hi everyone. So our last lesson on fields, last lesson for this area of study, and it's going to be about comparing fields. So we've looked at our gravitational, electric and magnetic fields. We've looked at different properties of them, and throughout doing this unit, I've drawn a few comparisons between the fields. Today we're just going to be doing a bit of a comparison of them in terms of things that we haven't quite spent much time on yet. So this stuff's pulling from chapter 2.5. We kind of skipped over this and left it until the end. If you go to the end of chapter 2.5, there's a convenient table summarizing the differences between the different fields in terms of how you calculate the electric and gravitational field strengths and the forces on different objects. And you can see analogies between those equations when they're set out nicely in that table. What I'm going to be focusing on today are some of the different types of terminology that we use when we talk about fields and basically categorizing the different fields as fitting into one category or another. So we start out using a bit of notation that we've talked about before, which is that we can sort fields as being either monopoles or dipoles. And when we talk about gravitational fields, like the one here, it's always like one particular source of the field. It's going to be that there's one thing producing a gravitational field pulling into it. We call this a monopole as a result. And you can contrast that with a magnetic field, which always has to be a dipole. There always has to be north and there always has to be a south. You can't have just one magnetic monopole. Those don't exist in nature. So this one is always just going to be on its own. This one's always going to come in a pair. Mono means one, it's on its own. Di means two, so it comes in a pair. Electric fields, we can have them as being like monopoles, just like the gravitational field here. Here is the field of a charge, a single charge on its own. So this is a monopole field. Or we can have the field due to a positive and negative charge together. This looks pretty much like the magnetic field of the magnet over here. This is a dipole setup because we've got two charges. And you could have a positive and a positive or a negative and a negative. The point is that you've got two things and the field that is produced by those two things together is sort of like a combination of them. So this would be a dipole electric field. This would be a monopole electric field. Now, next bit of terminology, one that's a bit, I feel this one's a bit easier, is that fields can be classified by their shapes. Now, if the field lines are all kind of radiating straight out from a single point, like in this positive charge, it's electric field here, we would call this a radial electric, or just radial field. So it's pointing outwards from the object. It's pointing outwards from the center, pointing out radially. That's where the name radial comes from. If the field lines are all parallel to each other, like between these positive and negative plates, then the field is linear. So here they're not parallel to each other, here they are. This is an electric field and so is this one, but they have different characteristics in terms of their shape. So we'd say that one is radial, one would be linear. Now, we can also talk about them in terms of whether the field strength is the same from one point to the next or whether it's going to vary from one point to the next. Now, in a capacitor or just between two plates like here, it's the same picture as before, but looking at a different property of this field, at any point between the two plates, you're going to get the same value for the electric field strength. And because of that, we're going to classify the electric field in here as being uniform. It's the same from one point to the next, same in terms of its strength, same in terms of its direction. If you have something like this gravitational field, if I measured the gravitational field here, that's going to get me a different value to if I measure the gravitational field strength out there. So because the field strength varies from one point to another, we would call this a non-uniform field. Now, the field would be the same, say, from here to there. If I keep my distance from the center of the Earth the same, I'm going to experience the same gravitational field strength. So it's not going to change it's not going to always change if I go from one point to the next. If I walk along the Earth's surface, gravitational field strength is going to remain approximately the same. But within this field, if I go from one point to another, then I would get a different field strength as I move towards or away from the Earth. So non-uniform as a result. And the very last one that we look at is that head and shape. And I should have highlighted the words or made them bold, but I didn't. If the shape and strength of the field do not change over time, the field is static. So if I've got the electric field produced by this positive charge, and I was to take a recording of the field at different locations around it, and then I was to come back later and do the same thing, how strong is the field here, for example, I'd get the same numbers because the field's not changing over time. It's what we call a static field. It's just, it's staying the way it is. By contrast, if the shape or the strength of the field changes over time, the field is what we call dynamic. And I tried searching for a GIF or a video to give a nicer illustration than text, but couldn't find what I was after. It says that an example would be the magnetic field produced by a current carrying wire as an AC current runs through it. So I don't have a wire with me. I'm just going to use this set of headphones to illustrate a wire, if I can untangle them. So you remember that when we talk about the magnetic field of a wire, it's in the form of concentric circles around the wire, and we determine the direction of those circles using our right hand grip rule, thumb in the direction of the current and fingers curling in the direction of the magnetic field. So if I change the strength of my current, I'm going to get a weaker magnetic field around my wire. The stronger that current through the wire is, the stronger my magnetic field would be. If I change the direction of my current, going down rather than up, then my magnetic field lines are going to be pointing in the opposite direction. So if I've got an AC current where it gets stronger and then it changes direction and gets stronger in that direction, where it's basically like a sine graph in terms of how strong it is, if I had an AC current running through my wire, it would be constantly changing in strength, my magnetic field, constantly changing in its direction. As a result, we'd say it's dynamic. It's not staying the same from one moment to the next, but it is constantly changing. So these are another two different ways of describing fields, whether they're staying the same over time and are static, whether they're changing and are dynamic. A bit of a side note, going back to something that I forgot to mention earlier, and I've brought this up before, but it's also useful to keep in mind. When we've got this set up here, we've got a uniform electric field within the two plates. If we wanted to get a uniform magnetic field, then we'd use one of the solenoid setups that we've looked at in previous lessons, where we've got a bunch of loops of wire together, and we said that within the loop of wire, within the solenoid, we've got a constant magnetic field. So here we've got a uniform electric field. If we wanted a uniform magnetic field, we just use a solenoid. This setup and the solenoid are kind of contrasting with each other because they both produce a uniform field inside them. And I think that's it. Those are all the bits of terminology you need to know. Like I said, if you want to get a better feel of a summary of what we've done and how the fields contrast with each other, go to the end of chapter 2.5. There's a nice table there that lists all the different properties of fields in a way that helps you kind of contrast them, but I feel that's something that's best left up to you. So you're finishing off chapter 2.5. I don't think there are any Ed Rollo questions for this chapter, so just make sure those questions are being done. Keep in mind that our next lesson is going to be the one on the SAC. The next lesson is going to be the SAC. There'll be more details about that released through Teams. You'll be doing it through Teams. That's where you'll get your instructions about the SAC from, and it's where you'll be submitting your work through. So just keep in mind that's going to be coming up in the next lesson.